Good day everyone, my name is Ron and let us answer some thermodynamic problems. A compressor is used to cover the pressure drop during the transportation of natural gas between two compressor stations. The inlet temperature of natural gas is 298.15 Kelvin, inlet pressure is 5.5 megapascal, and the compressor pressure ratio is 1.5. 1 million normal cubic meters per day of natural gas with the following composition of 92% methane, 3% ethane, 2% propane, 2.5% nitrogen, and the balance is carbon dioxide. Calculate the outlet temperature or the temperature of the gas at the compressor outlet, polytropic head, and the power required if polytropic efficiency of the compressor is 76%. So, going to a diagram of the representation of the problem, the inlet conditions is that its inlet feed is a natural gas with inlet pressure of 5.5 megapascal, 298.15 Kelvin. Volumetric flow rate is 1 million cubic meters per day, and respective molar fractions. So you might be wondering why we use molar fractions instead of mass fractions for this substance if it does not specify. Well, that's because for gas, as a rule of thumb, for gas mixtures, it is easier to understand and visualize volumes and mass, where for solids, it is easier to understand volumes and moles, while for solids, it's easier to understand in terms of mass only. Hence why we use the mole fraction instead of mass fraction for gas mixtures. So we have 0.92 mole fraction for methane, 0.03 for ethane, 0.02 for propane, 0.025 for nitrogen, and the balance is just simply the summation of all known mole fractions minus subtracted by 1, and we would have a balanced carbon dioxide mole fraction equating to 0.005. Then for the outlet is compressed gas, natural gas to compressed gas. It's the compressor is the unit operation in question to an outlet pressure of 8.25 megapascal. How do we calculate 8.25 megapascal? Well, noting that the compressor details, it is assumed that the compressor ratio has a formula or has a value of 1.5. The compressor ratio has a formula of the outlet pressure P2 over the inlet pressure P1, which is shown here. Since we already know P1 and we know the compressor pressure ratio, which is 1.5, it is a simple algebraic method to find P2, which is 8.25 megapascal. Then eta, or the efficiency of the compressor, is 0.76, and we must note it as polytropic. This is very important when trying to solve it using computer simulation. Then we need to solve this problem using DWSim. So to start, let us go to DWSim. We create a new process model. Then we need to specify our inlet property, not really inlet, these first system properties. So what are our compounds? Simple methane. So we'll search here methane. Include ethane. Include then propane. Insert include nitrogen, and lastly carbon dioxide. Double check methane, ethane, propane, nitrogen, carbon dioxide, methane, ethane, propane, nitrogen, carbon dioxide. Alright, everything looks good. Now for the property packages, another rule of thumb you should know is that for water component systems only, we use steam tables. For other compounds that are liquid in nature, we use the NRTL property package. And lastly, for other compounds that are gaseous in nature, such as this problem given here, we use the Peng-Robinson method. So we add this property here, we click next. Then we need to specify our customizable system of units. Our pressure is megapascal, so we put here MPa, and also our pressure difference in terms of MPa. Then the temperature is in Kelvin, so we'll put here as K. Then the volumetric flow rate must be at cubic meters per day. So volumetric flow rate is cubic meters per day, and essentially that is it, and we are ready to simulate the problem. So the unit operation being discussed here is a compressor. So we go here, pressure changers, compressor. Then DWSim will provide all the streams for us automatically. That's the beauty of DWSim. Next, we need to rename it properly. So we have the inlet, and we have the outlet, and this is the energy requirement. Remember, that those who require energy to function or electricity to function are pumps and compressors, respectively. And turbines produce energy. They don't need energy to use because they produce energy or electricity. But for compressors, they need energy or electricity to function. Alright, so let's specify our inlet conditions. So going to the diagram, our inlet natural gas is 5.5 megapascal. Sorry. Okay. 5.5 megapascal. Then a inlet temperature of 298.15 Kelvin. Okay. Then a inlet volumetric flow rate of 1 million cubic meters. So here, cubic meters per day volumetric flow rate. So 1 and 6 zeros, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Include and inlet conditions. And we need to specify the compounds. So we already defined the mole fractions. So 0.92 for methane, 0.03 for ethane, 0.02 for propane, 0.025 for nitrogen, and 0.005 for carbon dioxide. How do we know if the values we include here in the mole fractions is correct? Well, it is as long as it is equal to 1. If it is equal to 1, then this is correct. Before we continue, we must always press accept. Do not forget to press accept or else you will acquire the wrong solution. So when you press accept, this means that these amounts have been already inputted in the system. So even if you change into different options or unit operations, when you click on it again, it is now specified on the problem above. Okay, then we go now to the compressor details. So for the compressor, remember, the reason why I told you that we need to understand polytropic must be very, very important to take note of. So that's why we put here polytropic. Because having an adiabatic process will yield a different result. So we'll put here polytropic. Then an efficiency of 0.76 or 76% include. Then what we aim is an outlet pressure of 8.25 megapascal. So we have the calculation type, outlet pressure, 8.25 megapascal. And essentially we have solved the problem. So what do we need? So essentially we need the temperature of the gas at the compressor outlet. So the outlet temperature is 235.986 Kelvin. The polytropic head, so we can find that here in the compressor box. So the polytropic head is 55,681.46 meters. And lastly, the power required for everything to function is here, 35,973.90 kilowatts. Alright, so going back, we have solved it using DWSIM. So the outlet temperature, polytropic head, power requirement. Let me double check, 335.986. Yes. Then 5,681.46. Yes. And power requirement 35,973.90. So, we need to know if this answer is logical or not. How is this answer logical? Well, in terms of the outlet temperature, we know that this answer is logical by remembering our gas laws, specifically Gay-Lussac's law. So what is this law? This law states that the pressure is directly proportional to temperature under constant volume. Meaning that as pressure increases for gases, this is only for gas, so as pressure increases for gases, temperature also increases. And if you can remember that our inlet temperature is 298.15 Kelvin, and what we calculated or what we simulated from DWSIM is 335.986 Kelvin. And if it is not up to you or me, that is a greater value than the inlet one. And since pressure also increases by definition of the given, and temperature also increased as a result of the simulation, this means that it follows Gay-Lussac's law. Therefore, this answer is logical and in nature. But what about the polytropic head? How do we know if this polytropic head is a logical answer or not? Well, according from a simple definition for a polytropic head can be found from chemicalprocessing.com. It states here that an increase in centrifugal compressor speed will result in an increase in compressor polytropic head by a value equal to the square of the speed. The polytropic head is a function of pressure ratio across the compressor and therefore will result in a pressure rise, assuming the inlet pressure is not changed. Might be hard to understand, but in simpler terms, the higher the pressure, the higher the head. Why is it so? Because the pressure acts as a push force. The higher the push force, the higher the distance the fluid or the subject in question will travel from one point, which is the starting point, to another, which is the final point. Sometimes we refer to the head as the distance on how a certain liquid or a gas travels in a certain time, at a certain area and place. And since if the higher push force or the pressure is very, very much high or very powerful, then as a result, the distance that is traveled will also be very, very high. Next, lastly, for the power requirement, how do we know if this value is logical? 35,000 kilowatts, it might be a bit illogical given its vast value. However, it says here that all compressors, remember I said earlier, compressors and pumps consume electricity. All compressors consume electricity. And another condition is that the greater the initial conditions of feed, mass or volume flow rates, the greater the energy is required to process it. What does this mean? Because remember, our given is 1 million cubic meters per day of feed. 1 million. One cannot comprehend the amount or the vastness or the largest amount when you're seeing it in a physical sense. 1 million materials, 1 million amount of materials being processed in a singular unit operation. It makes sense that it requires a great amount of energy just to process it to our chosen outlet conditions. So 35,973.90 is a reasonable energy requirement to process 1 million cubic meters per day of natural gas. And also take note that the power greatly coincides with the amount, not only in terms of volume but also in terms of mass. Simply put, in order for a machine to operate, we need to know its capacity or its maximum amount to produce. However, in the simulation, it's all ideal in sense, so we assume that the capacity is limitless. But in a physical sense, normally we correlate volume to mass or mass to mass. Then, if the mass of the feed is very, very heavy, so imagine carrying a very, very heavy book, such as this example. I'm currently carrying my textbook, and it is very, very heavy. That means, in order for me to lift this book, which is my Chemical Engineering CHE Paris Handbook, 9th edition, I need to exert an equal amount of force or an equal amount of power to lift this book up. Now, in the sense of a compressor, if the feed is 1 million cubic meters per day, then an equivalent amount of power must be needed to accommodate that amount of cubic meters. So it's just another sense of what I said earlier, but in a more analogical manner. So, this means that all three of these answers are logical and are under proper theories, lessons, and accurate results.